Hi, my name is Praveen Vegala. We will be talking about video classification today. The primary objective of this project is to classify a video into sequence of actions. For this, we will be using CNN for the feature extraction and LSTM followed by dense layers for the actual classification. The implementation is based on Inception v3 with pre-trained ImageNet weights for feature extraction. And we are only going to be using the feature extraction part of it. That is the dense fully connected layer for the classification will be removed. And for the training and validation videos, we will be using UCF 101 dataset. This has about 13,000 videos categorized into 101 categories. For testing, we will be using a dataset from Kinetic 600 dataset. This is the hardware and software that was used for training and testing. Overview of the steps. So we first download the datasets, lay them into appropriate folders, convert the videos into images using FFmpeg. We then extract the features using Inception v3 from a downsampled set of images. We will be downsampling them to 40 per video. And then after the features have been extracted, we then save them into NumPy files. We then use these NumPy files with various hyperparameters to figure out the best optimal model when training. And we will be using a min validation loss as a training metric. And once we have a trained model, we will use this to segment a new video stream, rather than test video streams, into a sequence of actions or categories. Here's the Inception model where we just take the top portion, or rather the bottom portion of it, which will get us the features. It has an input shape of 299, 299, which is what we will size our input images as well, and has an output shape of 2048. The classification layer has an LSTM layer with 1024 neurons, followed by a dense 512 neuron layer, then a dropout, and another dense, final dense layer. It's a softmax layer, which will then classify the streams into 101 action items. So each of the video sample is downsampled to 40 images per video, and that would be the number of time steps for LSTM. And 2048 comes from the fact that the feature extraction from Inception gives you 2048 as the feature set. We will now actually go through the Jupyter Notebook to go over the actual code as well as execute the code too. And so let's first clear the. So the initial section over here tells us what we are, or rather how the data set is laid out. So here are the various URLs to download the data set, and also gives you the steps to lay out the data appropriately. And so this covers all the details in terms of how the data is laid out and what are the pre-steps that are required to get the entire training process started. So skip this for now. Here we import the relevant and probably some irrelevant Python modules. And so here's a key over here. So the training and as well as the prediction takes a long time. So we have a knob to decide whether to actually go through the training and the prediction. And we won't be doing that right now because it's going to take a long time. So we have already saved the models as well as the results of some of the predictions, which is what we will load as part of this demo. So here, setting up the various directories that are required to execute and after which. So here's the data preparation phase. What we're essentially doing over here is we are splitting rather we're copying the data into appropriate train and test data sets. And let's move on. And as you can see, it's not in it's in demo mode right now, which is why we'll end up not executing this code. And here are a bunch of helper functions to convert video to images. And for that, we're going to be using FFmpeg. And FFmpeg takes a while. I mean, given the large data set, it takes a while to generate. So what we end up doing over here is we parallelize it using 16 threads. And we will not be generating the images. It has already been pre-generated for us. So let's go on. And here is where we're setting up the sequence length to be 40, the features, and the classes, and so on and so forth. More functions to do the preparation of the data as well as feature extraction. So here you could see the get model function is where we're getting the Inception v3 model, and then we prune the top layer out. And all that we care about is just the feature extraction part of it. And so here are a bunch of functions, and this function, the genseq function, is the one that will generate the NumPy arrays, a sequence, or rather it generates a sequence of NumPy arrays, which is what we will be using for training the classification layer. And so the save features does what's needed. And we go. So let's take a look at this. So here we're loading the dataset meta. So you can actually see the 13,210. Here we actually lose some of the samples. The reason being is we've set a sequence length of 40, and any video that's smaller than that, we ignore them. So we have lost some samples due to that. Now this YouTube meta is some 10 random videos that we got from the Kinetics 600 dataset. And the way the metadata is laid out is that's the format that's being used. And let's see, what was it going to do? So this is the phase where we would actually save the features as NumPy arrays, but we're not going to be executing it since we are in demo mode right now. Now we are ready to train and evaluate the model. So here are the various functions to convert them into one-hot encoding for the classes. And we load the data, various helper functions. Here's the actual classification model. So we have a sequential model. So it's an LSTM followed by a dense layer, followed by another dense layer. So as you can see, I've been experimenting with a few other architectures, but then most of them, or rather all of them, the other variation that I've tried, were giving much worse results. So we're going to be sticking to this architecture, and this is the train model, the actual training, where we are saving the model for the validation loss being the minimum, and a bunch of helper functions to plot and whatnot. So here we actually start the training. So now we're going to load the data. This will take a few seconds to load the data. And here we're loading the entire data set into memory, since I have about 32 gig of memory, and if memory is a constraint, we could use a data frame generator. As you can see, we have about 94,000 training samples and 3,700 testing or validation samples. So this is the part where we're trying to figure out what's the best model, given the various parameters that can be tuned. And here we're kind of disabling the whole thing by saying that LSTM is an empty list. And what we're doing over here is getting the various models that have been pre-trained. So the output is kind of cluttered, but you get the idea. So we're saving both the history as well as the models. So for example, this is history for that, and then we save the model and so on and so forth. Going to the next thing. So here we're going to plot the model history for the various models. It gives us an idea as to which models are converging or which models are not, but it's kind of tough to figure out from these plots as to which is the most optimal model. So we will instead do it slightly differently by actually running the, we'll do a couple of things. So here what we're doing is we only have the history saved. So from the history files, we will figure out which one has the least validation loss, and then we take that. And so from the history, we determine that this is the model that is the best from a minimum validation loss point of view. So that's one way to do it. Another way to do it is we could actually take all the 16 models that we have and run the validation data against it. This is data that has not been used as part of training. And we could then evaluate the model from that. So even this is a prediction loop, which takes a long time since there are quite a few, there were 3,800 validation samples, and each of the validation sample converts to 40 images. And so that's quite a bit of images that need to be predicted. So we will not run the actual evaluation, but instead use the saved results that we have. So from this, we get the various predictions, the top end predictions. Based on this, here we get a slightly different model, which is LSTM with 2048 neurons. But the differences are small enough, and then the training time, in terms of the actual training time, 1024 is a much more faster in terms of the training time itself. So we will stick with 1024, and that's what we will use for the next. Here we are actually loading the module, the model which is the best as determined earlier. At this point, we're now ready to evaluate the model on the unknown data set that we got from YouTube. So here are a bunch of functions that help us predict and give us meaningful results. So like one of the interesting functions would be the video time sequence and the video overlay time sequence. So this gives you a sequence of actions with the start time, and the video overlay time actually overlays the actual action onto the video, as we've seen in the 2-minute presentation. So here we're getting the frame rates, and the frame rates are different for each of the videos, so we need to take that into account. And so we're going to start with horse riding as a first example. And here, if you the class frequencies tell you as to what are the actions that are most occurring within a given video. So here we see for the horse riding, the general horse riding video, we see a frequency of 8 for horse riding and so on and so forth. And here's a time sequence for the various actions. And we could also, I don't know why this video has not loaded. Let's use the one from a standalone terminal. So that's the video that we saw earlier. So where it actually predicts as horse riding and so on and so forth. And you see a bunch of misclassification in the sense that this is not soccer juggling clearly, but it's to do with the categories that we have in our training data set. Let's move on to another video. This time we'll try it on juggling. So here you actually see that the juggling frequency is pretty good. And I don't understand why we're not getting the video. Let's go back to the command line. So let's actually do this. One data set. So you can clearly see it's juggling balls. And then somewhere in between, we will see as the video switches a bit, it's classified as yo-yo. But that's all right. So overall, we see reasonably good results. So now what we could do is we could run this on all the the 10 videos that we have, and get an idea as to what the frequency. We get a general, for example, the bowling video, it's completely bowling and so on and so forth. And so this gives us a general idea as to what's going on in a video as a time sequence. So let's go on to. So all in all, we did reasonably well given the limited training classes, our action classes that we had, we've done a reasonably good job in the whole prediction of the sequence of actions in a given video. And there are certain things that could be improved upon. For example, we are segmenting each of those test videos as 40 frames for each segment. Instead, we could do something like a sliding window. And we could also probably use a much better model to begin with. So there are a few, the scope for improvements over here. But nonetheless, given the simplistic model, we have actually done reasonably well, I would say. And so the applications for this are numerous. I mean, you could use it in surveillance monitoring system, for example. Instead of having a person look at 10 different video screens for monitoring anomalies, you could actually use this kind of a mechanism to say whether a particular series of videos are valid for a given location, and so on and so forth. And so the next, I've been taking it to another level. If you were to treat this as a sequence of words or actions that have been generated, we could potentially use this for higher level learning. For example, if I were to see jumping, running, etc., in a sequence of events, and that's classified as sports event, for example. So you could do higher level learning from a given video actions and come up with a meta level construct for the whole thing. So most of the details are covered over here in terms of how the data is laid out and what needs to be done to get the whole model to be trained and tested. And thanks a lot for your time.